And for fourth session, we have Professor 𝗕𝗵𝘂𝗃 Nayak. And Professor 𝗕𝗵𝘂 Nayak is currently Associate Professor of Physics at 𝗕𝗪𝗂&𝗛 deemed to be University at Bhubaneswar. Now, she has postdoctorate from IIT Bhubaneswar. She was a research associate at NIT Rourkela, and she has also PhD from NIT Rourkela. Her broad field of expertise is in experimental condensed matter physics, and she has been awarded with DST Women Scientist Award, Best Presentation Award from BARC, and her 10 years of research experience ranges from ferroelectric materials, multiferroic materials, supercapacitors to metal matrix composites. And she has teaching experience of 7 years and 37 publications to her credit. So please let's welcome Dr. Professor 𝗕𝗵𝘂𝗃 Nayak. Ma'am, the screen is yours.
Okay. Thank you, Dr. 𝗕𝗧𝗃, for your nice introduction. And thank you, the committee members, Dr. Kirtis and Dr. 𝗕𝗧𝗃, to give me the chance to present my work here. And first of all, good evening to all. So now I am presenting the future direction and emerging trend in ferroelectric systems. So before starting the future direction and why the ferroelectric metals are used in a different electronic system, so first of all, we have to understand what is the ferroelectric material. So now we are using different electronic systems, which are used now. We are using the Samsung mobile, then iPhones, then previously we have used the Nokia mobiles. So day by day, the data storage is enhancing, and in that the ferroelectric metals are used. So first of all, we can say that the ferroelectric metals are used for the data storage. Data storage means ferroelectric metals can enable the non-volatile ferroelectric memory storage that allow for the data access and lower power consumptions occurs, and which is crucial for the electronic devices. And the second thing we can say that the ferroelectric metals are used for the sensors. So sensors means the sensor can exhibit it has the high sensing capabilities, and we can make the ferroelectric metal to a sensor material so that it will be ideal for the various applications that include the pressure, temperature, and also it is compatible to the environment. And the third one is the energy harvesting. Now this is the recent topic, or the emerging topic of the energy harvesting. So what is energy harvesting? That means the ferroelectric metals can convert that mechanical energy to the electrical energy, and which is essential in developing the self-powered devices, and the system is sustainable for the energy solution. So basically we can say that these type of metals are used for the data storage, sensor, and also the energy harvesting material. So coming to the second slide. So now this is the technological application. The first one here I am showing.
Ma'am, ma'am, sorry for interruption. Ma'am, please make it full screen.
Okay, sorry. Just 1 second.
Okay. Thank you, ma'am.
Okay. So coming for the coming for the technological application, what I said, the ferroelectric metals basically used for the data storage, sensors, and the energy harvesting material. So the first figure here I can show that the non-volatile ferroelectric memory, random access memory. So that means the previously the computers are made on that basis that when you are switch of the computer, that automatically all the data has gone. But now if the we are switching of the computer, the data already exists, and the memory is not lost. So that we can say that non non-volatile ferroelectric random access memory. And the second one is it is used in the sensors, in the piezoelectric sensors. So later we can discuss what is piezoelectric sensor, what is ferroelectric sensors, and that one. So here coming to the introduction. So here I have written the ferroelectric has the spontaneous electrical polarization of the material that can be reversed by the application of the electric field. That means that the ferroelectric material is such type of material or such type of dielectric material, and in that the spontaneation electric field can be exist. So what is dielectric material? Dielectric material, that we know that the capacitor in that dielectric material is present, and if we apply the electric field, the material get polarized. How it is polarized? So that different types of polarization is there, and the electronic, ionic, then orbital, and there are different types of polarization. So what is ferroelectric material? We can say that when you are applying the electric field, all the dipoles are aligned in the field direction, and if we remove the electric field, the in the material polarization that also exists. So that is called as the spontaneous electrical polarization. For that, the memory is not lost, and it is used for the non-volatile ferroelectric random access memory. So how we can confirm the ferroelectric metal? So if we take if we take a material and we apply the electric field, and we can get the P loop. That loop here, here it is on the P loop. We can get, if we can get such type of P loop, then we can say that it is a ferroelectric material. So that means in the means x-axis we have taken the electric field, and then the means y-axis we have taken the polarization. If we apply the electric field, all the dipoles are along the same direction, and if we remove the ferroelectric metal, that suddenly not comes to the origin, and it is means the spontaneous it is not coming to the origin, as the spontaneous electrical polarization exists in the material. And so that means to confirm the ferroelectric material, P loop or the hysteresis loop must must observe in that material, and it is, and all the, if we can say that the property of the ferroelectric material, it has the high dielectric constant, because I have already told that the dielectric material is, the ferroelectric material is such type of material, or it is a type of dielectric material in which the spontaneous electrical polarization exists in the material. So, and the second is when we are applying the temperature, all the ferroelectric materials, there means if we take the dielectric constant with respect to temperature, the dielectric constant gradually increases, and at a certain point the dielectric constant decreases. That means the polarization, all the dipoles are not along the same direction, it will be in the reverse direction. So that means what the in the crystallographic changes, that means the some phase is changed, that is ferroelectric to the paraelectric, and in the paraelectric phase we cannot get the ferroelectric material, and means ferroelectric phase. So here so we can say that the three properties of the ferroelectric metal, we can say that this is the switching speed and the energy harvesting. Thermal stability means how it is sustained up to the high temperature, not only the room temperature, up to what temperature is sustained. And the dielectric constant, that means it has the high dielectric constant, and mechanical flexibility, that we have already I have already told that. And domain engineering means how much electric field we are applying, so that the all the dipoles along the same direction, and also it depends upon the temperature, then the external field, and also the temperature, and also the external electric field. So coming to the piezoelectric material, all the ferroelectric metals are piezoelectric, but all the piezoelectric metals are not ferroelectric. That I told that the ferroelectric metals are used in the sensor application. So sensor application means that you call say that is the piezoelectric material. So that means when the polarization generated by the mechanical stress. I have already told that when you are applying the electric field, the dipoles are aligned along the same direction and the polarization occurs. Not only the electric field we can apply, if we apply the mechanical stress or if we apply the stress, then the dipoles are aligned along the same direction, and that type of material is called the piezoelectric materials. And that piezoelectric metals are used in speaker, ultrasonic generator, actuator, and so on. Then the pyroelectric metals. So before that, I have already told that if we apply the electric field, then the polarization along the electric field direction, and also if we apply the pressure, then the polarization occurs, and the polarization and the net polarization occurs in that material, that is called as the piezoelectric. So what is pyroelectric metals? Not only the electric field and the pressure or the stress we have to apply, if we apply the temperature, also the the polarization occurs in that material, that is called as the pyroelectric metals. So in the recent trend of the the researchers are taking such type of material which have the better ferroelectric metal, so that we can use the ferroelectric metal to non-volatile random access memory. And if we can take such type of materials, and if we and the same material, if it gives the ferroelectric, sorry, piezoelectric and pyroelectric metal, so that will be the good or the excellent material. So research is going on this direction, and people are day by day they are preparing the sample, different characterization they have done, and they are finding out what is the piezoelectric constant, what is the property of the pyroelectricity, and how much the ferroelectricity exists in the material, so that it will be used in different cases. So now the recent challenge in the ferroelectric metal, we can say that high efficiency, then versatile application, temperature stability, that I told that not only it will be used in the room temperature, if it is used for the high temperature, that is 500, 600, so that material is a good material. Low power consumption, then processing complexity, then cost consideration, that is this cost consideration, this one is the most important factor nowadays. And the material degradation, degradation means up to how much it will perform, means the same property we can get, and if we use the material again and again, the property of the material degrade. And limited scalability. So coming to the different types of ferroelectric metal, there are basically 4 different types. The first one is the perovskite type material, pyrochlore type compounds, then the bismuth oxide layer, and the tungsten bones type compound, organic polymers and ceramic polymers. And these are the different examples I have written. And all of you know that in the barium titanate, which one is the best ferroelectric metal, and also the PJT, PMD, and a PJT, PMD, that one is the lead-based ferroelectric metal. Now the environmental, now lead is the it is poisonous, and for that now research is going on to the lead-free ferroelectric systems. So here in the barium titanate from 1952, now people are working on the same material, and different in the different sites they are doping, they are substituting on different material, different elements to get the better properties. And not only the perovskite material, bismuth oxide layers structure, this one is the best material, and the tungsten bones type, this material, in this metal people are also working on that. And also the pyroelectric metal, people are working on the pyroelectric type compounds. But as so many research is going on the perovskite material, so we are thinking about the bismuth layer structure compounds. And means we are trying to prepare this type of material, and what are the different properties that I told, that ferroelectric property how much, then piezoelectric property how much, then what is the dielectric constant of that material, we have also characterized all that. So if I told that the bismuth layer structure, the general formula that we have written, the bismuth oxide layer, and AM-1, BMO3M plus 1. A is the A side cation and B is the B side cation, O is the oxygen. And this metal is also called as Arrhenius compounds. The A side is 1, 2, 3 valency cations on larger side, that means the strontium, calcium. Then in the periodic table, the strontium, calcium, then barium, these are the A side is present, and B side is 4, 5, 6 valency cations. That means the titanium, then tantalum, niobium, these are the 4, 5, 6 valency that this is present. And the different advantage why you have taken this type of material for the different advantages, that is fatigue free. Fatigue free means up to 10 to the power 12 cycle this metal is means the property is not degrade. That I have told that this is the means why you have means whenever you are choosing a material, you have to choose a means fatigue free, means the number of cycle is more. So this one is the fatigue free material, means up to 10 to the power 12 cycle the metal's property is not degrade. And low leakage current, if the leakage current is low, that means the property will be more, means the good property we can find out. And fast switching, and in why we have taken this type of material, because in the this is nothing but the perovskite material that I have already told, that means AbO3 type material, but in the AbO3 the bismuth layer is present, and the bismuth oxide layer that act as is okay, that bismuth oxide layer that act as an insulating paraelectric layer. For that, the means it has the fatigue free, or the means it sustains up to 10 to the power 12 cycle. And for these advantages, the metals you use for high transition temperature devices, regenerator application, non-volatile ferroelectric random access memory, and high piezoelectric devices, pyroelectric sensors, and other electric and magnetic devices. So here I have shown some different figures of the bismuth layer structure. In the first figure, we can say that the blue one, so that is the perovskite block, but in the means that's the square type, that vacant one, this is the bismuth oxide layer. In the first figure, so that is this one is the bismuth oxide layer, and this is the perovskite block. That this bismuth oxide, as this is one layer is present, so this is called the one layer structure. And the second figure, this is the bismuth oxide layer, and this is the this one is the bismuth oxide layer, and this one is the perovskite layer. So second one is the two layer structure, and this one is the 3 layer structure, and this one is the 4 layer structure, and this one is the 5th layer structure, 5 layer. If the layer is more, then the fatigue is means it has the fatigue free property, or the property is good for the material. So here I have means this is the 5th layer structure. But now the question is from the 1 layer, 2 layer, 3 layer, 4 layer, and so on. And but we cannot extend the layer up to the means higher of the 5th, means 6th layer the metal does not exist. But among the 1, 2, 3, and 4 layer, so which one we have to choose? We have to choose. Then we have go to the literature, and we got the different materials, and different researchers are work on that material, 1 layer, 2 layer, 3 layer. So among that, and we have found out one material which one is the best according to the property. So this is the layer, means in the left side I have written the compound name, and M is the layer, means 1, 2, 3, 4, 5 that we have written, and the next one is the dielectric constant, and next one is the transition temperature. D33 means piezoelectric constant, and P is the means polarization, and the number of cycles that we have written. And if we compare this table, this 1, 2, 3, 4 layer and 5 layer, we got the strontium, bismuth, titan, and the red one here, and this is the 4 layer structure. The room temperature dielectric constant is only written here, and the transition temperature is 530. That means the material can sustain the property of the material is in the property of the material, or the metal can sustain up to 530 degrees centigrade centigrade. Means our room temperature is 25 degrees centigrade, but the metal sustained up to 530 degrees centigrade. And the piezoelectric constant, how piezoelectric constant is that I told that for piezoelectric sense, how we can find experimentally, how we can find out it is a piezoelectric metal. That means we can find out a D33 value. If the D33 value is more, that means the metal is a good piezoelectric metal. So D33 value is 15 here I got. And the polarization that you have not mentioned here, but after performing the experiment, we have conducted all those things. And number of the cycle that I told that up to 10^12 cycle it exists. So among the different types of metal, we have chosen the 4 layer structure, that SBT, strontium, bismuth, titanate. And nothing that I have already told that this is a 4 layer. And first one, the merits of the material, it is lead free, that lead is poisonous. So now the environmental people, they have banned lead, and that we cannot use in many materials. And the next one is it has the fatigue free, that is 10^12 cycle. Then D33 value is 15, and coercive field, that is 52.331, and the polarization, that is 13.52 microcoulomb per centimeter square. High TC, that I have already told that. And the next one is written the tolerance factor and orthorhombic distortion. Why I have written the tolerance factor, orthorhombic distortion? Because to performing means to whenever we are conducting the experiments, the tolerance factor is most related to the electrical property, and orthorhombic distortion, that is also related to the electrical property. For that, I have mentioned here tolerance factor and the orthorhombic distortion. And this metal is used that different application that I have already told, that high TC devices. Now this metal is used in the aerospace engineering also, and recently we have published one paper, and based on that material, which means this one is used for the aerospace, means aircraft or the aeroplanes. So means coming to the different characterization part, we have prepared the sample. Then SBT, not only the SBT we have prepared, we have modified on the different sides, and also the strontium, bismuth, titanate, that I have told that it is nothing but a AbO3 structure. In the A side, strontium and bismuth is present, and the B side, titanium is present. And we have, first of all, we have prepared the sample, and not only the SB2 we have prepared, we have modified on the A side and the B side. A side means strontium. Instead of the strontium, we have doped barium, calcium, and in the bismuth side we have also doped as bismuth is 3+, we have changed this to lanthanum, gadolinium we have also made. And the titanium, in the titanium side we have also substitute the niobium, tungsten, like that. And here I have shown only the good property that I got the tungsten when we were placed in the bismuth, when we have placed in the titanium side. As titanium is 4+, but tungsten is 6+. Whenever we substitute the tungsten in the titanium side, the metal gives the better property compared to the pure SBT. So, and coming to the different characterization, so we have first we conducted the structural characterization. Then for the electrical characterization we have conducted, and also we have conducted the P loop, that whether it's showing the ferroelectric metal or not, and what is the polarization and saturation polarization, what is the remnant polarization, what is the coercivity. For that we have conducted the P loop. And not only for that, as it is a high temperature and the piezoelectric constant is also good, we have also taken the piezoelectric not only at room temperature but also at the high temperature. That means what is the thermal stability of the material, that also we found out. So for the structural characterization, we have conducted the XRD, that we have, means most of the people know what is XRD, means how we have prepared the sample. So let me explain. So we have taken the strontium carbonate, that is the powder form, and the bismuth oxide, we have taken that powder form, and the titanium oxide that we have taken on the powder form. And for the 10 gram preparation of the SBT, for the 10 gram, there is a calculation that is called the stoichiometric, and we have, according to the stoichiometric calculation, we have taken the strontium carbonate, bismuth oxide, and the titanium oxide in a weighing machine. Suppose strontium is 2.01 something, then bismuth is 3 point, then titanium is 1 point, and the total equals to 10 gram. For that, we have taken, according to that, we have taken, we are using a weighing machine, and we have just weighted the material, and we have to mix it in a agate mortar. So after that, we have ball milled the same powder in a acetone medium. Just we have taken the material, and in that we have in a container, we have taken the metal in a container. Then we have put the ethanol in that, and we have placed it in the ball milling machine. So later we will show what is the ball milling machine. That next slide is the ball milling machine is there. I am showing that one. And ball mill. After that, we have collected the samples, and we have collected the samples. Then we have calcined the samples, and calcined the samples, so that if the we have calcined the samples, so that if whenever the samples is prepared, calcined the samples means we have taken the samples and put it in a high temperature furnace. So in that, the oxide and the carbonate and the carbon dioxide that are evaporate, we can get the SBT material. And how we confirm the metal is formed or not? After the calcination, we have done the XRD analysis. And for the XRD analysis, I have shown. After that, we have let me explain first. Then we have to. Then I will explain what is the XRD result I got. So then after calcination, we take the XRD, and then after we have to mix the samples again, and we have make a different palette form, so that we can conduct the electrical characterization and electrical characterization. So in the XRD, here this is the XRD data, and from that XRD data we got the sample is pure SBT is formed. How we know that it is the pure SBT? So some JCPDS files already exist, and the peaks are the peaks what you mean, that is formed at 31, then 30, then 34, 35, all the matches in the JCPDS number 1. So we confirm that the pure SBT is formed. And not only we have prepared the pure SBT, that I told that we have doped in the tungsten in the titanium side. And in the titanium side, we have taken the different composition for the titanium, and for the different composition of the titanium, that is 0.02. Instead of suppose the titanium is 100%, we have taken the 2% of the tungsten, 2, 4, 6, 8, and for the 2, 4, 6, 8, 10, like that way. So for the tungsten percentage is 0.02, 0.04, 0.06, 0.08, and 0.1. This is the tungsten percentage we have taken. That means we have prepared the 6 samples, pure SBT, and also the tungsten doped sample of the different concentration. Then this is the XRD. Whenever we have if we place the tungsten in the titanium side, from the XRD analysis, we got that the pure SBT and the tungsten XPT, the XRD peaks are same. So that means it will not disturb in the structural, any deformation, and any structural deformation not happens in that material. So that means the pure structure is formed whenever we have placed the tungsten in the titanium side. But then we have done the Rietveld definement. So there is another analysis, and we have find out what is the lattice parameter, and what is the lattice parameter of the material. So lattice parameter means A, B, C, lattice parameter. Then we got that the lattice in the doped sample, lattice parameter gradually decreasing. Suppose that means for the pure one, if the lattice parameter A is equals to 5.42, and for the doping, in the doping concentration, the lattice parameter gradually decreases. And cell volume that is also decreases. So the reason maybe we found out that the reason may be due to the smaller ionic radius of the tungsten compared to the titanium. That the ionic radius I have mentioned here, that is 0.60, and the titanium is 0.61 angstrom. So we thought that maybe due to the ionic radius or the smaller ionic radius of the tungsten, the lattice parameter gradually decreases. So the next question is, if the lattice parameter gradually decreases, how it affects the electrical property of the material? What about the dielectric constant, and what about the piezoelectric constant? We have prepared, we have done the structural characterization, but our aim is not to prepare the material, how it is applicable in the different fields. So for that we have characterized the more, and how it is the structural parameter or the structural characterization, how it is related to electrical characterization, that also we have to find out. So this figure is the SEM figure, scanning electron micrograph of the pellet from samples. So from that also we got that in the doping sample, the grain size gradually decreases. So the first one, that is for the SBT, but in the latter one the grain size gradually decreasing. So that I told that so we thought that maybe due to the smaller ionic radius of the tungsten compared to the titanium, then the grain size gradually decreases. And also I know that the grain affects the electrical properties. Electrical property means the conductivity, and if we find out the conductivity, so that one is related to the polarization, means the P loop, and that conductivity is also related to piezoelectric property. So for that we further study the conductivity analysis. So this is the Raman spectroscopy, and from the Raman spectroscopy we got the different Raman modes and how it is related to the structural characterization, that also we have to find out. So coming to the dielectric study, and in that we got that, means we have taken the dielectric study in an LCR meter and the dielectric constant, and we have plotted the graph dielectric constant with respect to temperature, or temperature versus dielectric constant, and we got the peak one, the peak point, that is called as the transition temperature. That means the ferroelectric to the paraelectric stage, the transition temperature, that means on the temperature on which means a particular temperature, all the dielectric, all the ferroelectric materials, they got the paraelectric, and that is called as the transition temperature. And what we got from the dielectric study, we got the dielectric constant gradually decreases, and then we have to find out the the second graph, that is the diffusivity. Diffusivity means, so this is the calculation from the dielectric, we have calculated diffusivity. The diffusivity gradually increases, and that is 1.11 for the parent one, that SBT, and the diffusivity gradually increases. So means one of the advantages we got, that is the diffusivity increases. So why diffusivity increases? We thought that maybe the tungsten is present on the titanium side. For that maybe the diffusivity increases, and this diffusivity increases means the material may be a relaxer material. For that we have to calculate the means one advantages we got, that is the relaxer behavior. Relaxer means not only the temperature dependent we can use the material, but also the frequency dependent, means any frequency, if the material sustain for the if it gives the better property in the frequency range, we can say that it is the relaxer material. Any frequency related means it is the relaxer material, and we can use also as a relaxer material. Then you have to find out the ferroelectric property, and here this is the ferroelectric P loop, and the pink one, that is the P loop for the 0.01, and we got the saturation polarization polarization remain and polarization also increases in that material, and in that material that means the with the doping material, and it is highest for the 0.01, and with loss, the dielectric loss, if we compare the dielectric loss, that material has the lowest dielectric loss. That means one name we have the two, now we have the two advantages, that means relaxer property is good, and the second one is the means better ferroelectric material, means polarization is more on the doping material, that and it will be better for the 0.01 compound. Then we have to find out the relaxation, means impedance spectroscopy of the material. Impedance means what is the resistance, that I told that grains are present and grain boundary is there, and this grain and grain boundary is related to the resistance, and it is also related to the conductance of the material. And how it is means, how we have to find out, we have to find out the impedance, the real part of the impedance, and the imaginary part of the impedance. So real part and imaginary, here we have shown the means 0.00 and 0.01, and what I got, the impedance of the means doping material is more, and the doping material is more means the resistance is more, so we thought that the conductivity may be decreases, and that conductivity, due to the less conductivity, and the means the material gives the better ferroelectric property. And this one is the Коваль plot. Коваль means we have plotted the graph Z prime, Z double prime, and from that we have to calculate what is the resistance of the grain and what is the resistance of the grain boundary, how it is related to temperature. Means we have taken, means we have conducted the sample up to room temperature to 700 degrees centigrade. As I told that my material sustain up to 530 degrees centigrade, or the transition temperature is 550 degrees centigrade. So we have taken from room temperature to 700 degrees centigrade, and we have also find out what is the resistance of the grain, what is the resistance of the grain boundary, how it is related to the structural property, how it is related to ferroelectric property, and how it is related to the piezoelectric property. All the characterization we have done, and we have just correlate the structural property, the means all the parameters to the electrical property. Structural, we have correlated the structural with the electrical property. And after that, we have taken the SC conductivity. As I told that in the doping material, the resistance is more, so that means the conductivity is less. So here we have taken the conductivity. So there is different equations are there, and we have fitted the equations with the Johnson's power law, and for that we can calculate what is the DC conductivity and how it is related to temperature, and all those things we have to find out. And after that, and that means we have find out what is the grain resistance, grain boundary resistance, what is the AC conductivity of the material, what is the DC conductivity of the material, how it is related to frequency, how it is related to temperature. So after conducting all the experiments, we have found out what is the means piezoelectric constant of the material. So, and not only you have taken, generally people what they are doing, they are taking the piezoelectric constant and room temperature, but for the high temperature piezoelectric application, we have taken the find out the piezoelectric constant for room temperature to up to 700 degrees centigrade. So here I can say that we can find out up to room temperature to 500 degrees centigrade. So we got the constant piezoelectric property, means the DT3 value is constant. After that, the DT3 value gradually decreases. So that means we confirm that the thermal stability of the material, that means the material is sustained up to the transition temperature, and we can also use the material for high temperature piezoelectric application. So I have already told that recently we have published a paper for the high temperature piezoelectric sensor application for the aerospace engineering, and we proved that this material is used for the aerospace engineering, and these are the conclusions. And the grain size decreases from the ACM study, and the dielectric constant gradually decreases. Impedance, that grain resistance, grain boundary resistance, we found out, and we have correlated with the conductivity, and also we have correlated the conductance with the resistance values. And finally we find out what is the ferroelectric constant, what is the dielectric value, what is the piezoelectric value in the material up to a high temperature. So this is the next generation ferroelectric metal. So whenever that this metal I have chosen in the bulk metal we have prepared. So the next challenging is the you have to choose a material and you have to prepare the ultra thin ferroelectric film for devices. Means that for the device application you have to prepare the ferroelectric metal in the thin film. And the second one is how it is biocompatible. Means recently most of the means I have seen 2 to 3 papers through 2 to 3 papers in that the barium titanate, that metal, the nanoparticle barium titanate material is used for the cancer disease. So for that, not only this metal, how the ferroelectric metals is applicable for the cancer treatment. And we know that nanoparticles is the best example, or nanoparticles means if we prepare the nanoparticles it gives the better result. So for the biocompatible ferroelectric medical application, that is the now means all people know that, and the means if you have preparing a sample for the medical application, that will be the better. And the third level is all organic ferroelectric for sustainability. And fourth level is means whenever you have prepared the metal, the lead free is the best one. So you have to prepare and you have to compare with the lead based material. And the fifth one is multifunctional ferroelectric hybrid composite composite metal. Multifunctional means, as I told, that my materials, whenever I have chosen my material, that material shows different property. And different means multifunctional means one material gives the different application. One metal can be used different application, that is called as multifunctional ferroelectric metal. And the sixth level is doped ferroelectric enhance the performance strategy. Not only you have to prepare the same metal, then you have to dope some, as in the periodic table, so many elements are there, you have to try on that one. And if you give the better property, that you can also show that. And the seventh one, the ferroelectric nanostructure improve the energy harvesting. So this is the recent topic, energy harvesting. And the means the next level is the emerging computational method for designing. So now AI is the emerging trend, and people are using AI to find out which one is the better, which gives the better ferroelectric or multifunctional property. They are also using. So these are the references. Okay, so these are the references. Hello, Dr. Ishita.
Yes, ma'am.
So this is all about the recent topic of the ferroelectric metal. So if I have the if you give me more 15 minutes, then I will describe some different thing on that.
Sure, ma'am. You have time, sir.
Okay. So these are the references. So this is this topic that I have already covered, the ferroelectric material and how it is used in the different sectors. So we, as research is research is a very big platform. We have not not only the preparing the ferroelectric multifunctional material, and also we have prepared the aluminum metal metric composite for day-to-day life. So here and also we have taken the graphene on the mechanical and conducting properties of how it affects the mechanical conducting properties of aluminum. In most of the cases we have seen in our door, window, all that aluminum is used. So this is the outline. Means aluminum and application of the aluminum in different sectors. So how we will introduce the graphene in the aluminum, and why aluminum graphene metal matrix composite we prepare this sample, and what is the different methodology, result and conclusion. So coming to the introduction. So as we know that aluminum is the third abundant material in the Earth's surface, which one is 8.1%, and it has the high strength to weight ratio, and it has the light weight. For that, aluminum is used in that, or you are using aluminum slides, aluminum doors, aluminum windows in different sectors, and high electrical and thermal conductivity, non-magnetic and non-sparking, and insoluble in ethanol, water, and resistance. Although it has the corrosion property. Corrosion means it has the means whenever you are taking the aluminum, so it will be not means it is not just like the means iron, and that means aluminum oxide layer is formed on the aluminum, so it protects the for that it will be used for the means longer time, and easy to cast, and ductility is easy. So for that property, the aluminum is used for the aluminum. We are using aluminum foils, electrical wires, food packaging, cooking pots, used in mirror and the backside of the mirror, then decorative components, automobile bodies, engine parts, and so on. So, however, the application of the pure aluminum is very rare compared to its alloys. So, for that, we thought that not only the aluminum we can use, and also we have to make it metal matrix composite system. So, this is the limitation of the aluminum, though low melting point. So, that is 660 degrees centigrade, which restricts the maximum temperature at which it can used, and that means, and moreover it is very soft, and for that it is used in the means for that it restricts their application in automobile sectors and aircrafts, and means suppose in the automobile sector, means a stronger material are required, in that we are using the aluminum, we are preparing the aluminum metal matrix composite so that it will be stronger, we can use that metal in the automobile sector. So keeping this in mind, so we have prepared the aluminum metal matrix composite, and all of you know that graphene now people are using, the chemistry people, the physics people, the mechanical people all are using the graphene because it has the good property. So graphene is a high electron, means it means the conductivity is more, and the mechanical property is also good for the graphene, and it has the strongest material. So if we take the 1 gram of the graphene, it will be spread in the whole football ground, that all of you read in the books, and all that means it is already written that. So for that, it has the high electrical, so it has the high thermal conductivity and electrical conductivity. For that we have taken the graphene, and we have prepared the aluminum metal matrix composite for the automobile application. And not only for the automobile application, and for the to enhance the thermal conductivity of the graphene, means we have characterized the thermal conductivity, and we have made a prototype, that all of you know that in the pressure cooker, the lower part is the aluminum, and means we have made one pressure cooker, and just we have talked with the, means we have talked with the prestige, and they have, means whatever metal matrix means aluminum graphene composite we have prepared, and we have prepared, means we have made a prototype for the, means prototype for the that pressure cooker. We have made one prototype pressure cooker, and then we have to find out what is the thermal conductivity, that we have already done, and we have filed a patent on that. So coming to the how we have to prepare. So we have prepared in two different types. Means first one is the powder metallurgy method. In that, the same like the SBT, the ferroelectric metal, we have taken the aluminum powder, then processed, then compared, then sinter, then means we have find out the density, porosity, ductility, conductivity, all that, and different percentage of the graphene, that we have taken 0.0, 0.25, 0.5, 2 weight percent we have taken for the graphene. And this is the result here, and that I told that the ball milling, here I have shown the ball milling. The first figure is the ball milling machine, and the second one is the means ball milling jar, and the balls are stainless steel balls are there. But when we are preparing the ferroelectric metal, the stainless steel ball we are not using. In that, for preparing the ceramic metal, we are using the zirconia balls. But as this is the metal, we have taken the 10:1 ratio for the stainless steel balls. So in the jar we have put the 10 gram of the aluminum and graphene powder, and put the balls, and we have put in the ball milling machine for 24 hour for 10 hour, and the rpm is 300 rpm, and ball to powder ratio is 10:1. Okay, so the lower part is the SEM of the pure aluminum and the pure graphene. So before conducting the SEM experiment, we have taken the SEM graphs, and this is the weight machine. And the second figure that I have shown the after preparing the pellets, we have centered in that vacuum furnace. So whenever we have prepared the ferroelectric metal, we have taken a high temperature furnace, and that is not vacuum. But in the aluminum, when you have prepared the aluminum metal matrix composite, in that we have taken a vacuum furnace, because if you are not if you have not using the vacuum furnace, the aluminum oxide layer is formed. For that, for getting the pure aluminum, we have taken the vacuum furnace. And the third one is the pellet, that I have already told that. And first one is the XRD figure, means what is the purity of the sample, how the sample is formed or not, that we got. And the second one is the Raman spectroscopy, and here this is the figure shows the SEM graph, and how it is related to the what I got the SEM figure, that we also correlate with the thermal conductivity, electrical conductivity, and also the hardness. And he is one of my friend, Dr. Kedar, and he has prepared I have prepared the sample for the powder metallurgy method, but he has taken the aluminum, that raw aluminum rod from the Nalco, and he has melted the aluminum. Just I told that the melting point of aluminum is 60 degrees centigrade. So he has heated the sample above 660, so that the aluminum is melted, and one liquid is formed. In that, he poured the graphene powder on that, on the different percentage. Then after that, he on the different step, he has just taken that liquid to the different form, and the last one is the pellet or the rod shape is formed out. So then you have to calculate what is the density of the metal. As the density means, if the pores are present on the metal, the metal property will be degraded. So for that, we have find out the density measurement, and also the micro hardness. What is the hardness of the metal? That means we have prepared the metal for the automobile application in the automobile sectors. For that, the hardness is the most important thing. And this is the thermal conductivity and the electrical conductivity, that we got that means thermal conductivity increases up to 0.2 percentage of the graphene, and after that the 0.5 percentage of graphene. Then after that, it will be the property will be degraded. And so this is the UTM measurement. So coming to the conclusion, so we have prepared the aluminum metal matrix composite in two different methods. That one is the powder metallurgy method, and also the casting method. And the SEM, what we have got the SEM figure, and the density measurement, and the UTM measurement, all, and thermal conductivity, electrical conductivity, that we have related with the structural analysis. And we have also made one prototype for the aluminum metal matrix composite for the automobile application. So this one, the paper is published, but we are not even till now we have not filed any patent. But for the thermal conductivity, we have filed, already my patent is also published. So thank you. Thank you,
ma'am. Ma'am, please see the chat. Someone asking some question from the chat.
Okay.
Please.
Sir, where it is?
Dear ma'am, how do I obtain a 𝗕𝗫𝗄𝗣𝗔 number from any XRD peak? Chart.
Okay, so that so that 𝗕𝗫𝗄𝗣𝗔 file is also available in the database. So when means the XRD in the XRD means suppose Rigaku XRD is there, they have given one CD file that already in the means in the CD file 𝗕𝗫𝗄𝗣𝗔 file is means already exist. And in that system, the means suppose the XRD is connected XRD is connected with the computer. In that we means the installer already means install the and that CD in that system, so that we can get, suppose I am getting that peak. Suppose in the 30 the peak is coming out, so you have to find out the 30 peak is related to the iron or it is related to strontium. That we can find out in that system also.
Ma'am, Sankhamitra is asking, why are hafnium oxide based ferroelectrics considered a breakthrough for CMOS compatible ferroelectric systems?
Why?
Why are hafnium oxide HFO2 based ferroelectrics considered a breakthrough for CMOS compatible ferroelectric systems?
Ma'am, actually hafnium is the means rare earth element. Okay, generally the rare earth elements gives the better properties, I think so, but I have not worked on that terminology, that CMN what it is not means I am not clear about that system.
Okay, ma'am. And Monica Trivedi is asking, which instrument you have used for this study?
Which one?
I'm not sure. Monica ma'am, are you there? Hello, Monica ma'am, are you there?
Yes, ma'am. Yes, ma'am.
Ma'am, please ask question.
Dielectric and everything which was presented
so
earlier.
that is the LCR meter. Okay, so if you want to purchase one LCR meter, so the basic thing you have to means you have to note down that the frequency, that means from 1 hertz to 1 megahertz. Okay, and the second thing is the temperature, room temperature to means 700 to 500 degrees centigrade, it is also okay. So if you're taking the more temperature, so there are two things you have to check. First one is the frequency and second one is the temperature, and that all the means LCR, that means for the dielectric we can use the LCR meter. For the impedance we can also use the LCR meter.
Okay. Thank you, ma'am.
Any questions? Any other questions, please? Please, if you have any questions, please ask.
Hello. Good evening, ma'am. Myself, Dr. 𝗕𝗬𝗙. Ma'am, any idea about the costing of your furnace in this metal matrix composite making?
So that is 40 lakhs. So if you use the vacuum furnace, that we have purchased 40 lakhs.
40 lakhs is the so much amount, but within 20 or 25 lakhs.
And that is the 40 lakhs that I told that the means vacuum furnace. Okay, for the means when you have means for the powder metallurgy method, that another graph I have shown that the one of my friend is casting on that, so that that we purchase 8 lakhs.
Okay, thank you.
Ma'am, Sankhamitra is again asking, how can dielectric constant versus temperature studies help in device applications such as capacitors, ferroelectric
Yes.
memories, and sensors.
Yes. So, means dielectric constant versus temperature. Okay. So, whenever you are finding out the dielectric constant, means from the LCR meter, we can find out the capacitance value. Then we have to convert the dielectric constant. Okay. And we have to plot the graph for the dielectric constant and temperature. So, that means after certain, if you increase the temperature, dielectric constant increases. Then after that, the dielectric constant decreases. Right. And that means this is the tension. Suppose my tension temperature is 300 degrees centigrade. So then the question is how the dielectric constant is used for the capacitor application. So capacitor application means when the metal which have the high dielectric constant, that gives the better, because capacitance is directly related to the dielectric constant. So that means high dielectric constant is better capacitance.
Okay. Any more questions? Okay. Please ask if any questions are there.
Please wait for 2 minutes, otherwise you will wind up.
Okay.
Okay, ma'am.
Okay, thank you, Dr. 𝗕𝗧𝗔𝗟 and Dr. 𝗕𝗵𝘂𝗃 for arranging such type of FTP program, and also authored for conducting the authored in the offline mode. So in the offline mode, for that means I am eligible to present, because in the online mode so many work pressure is there. And also I thank to your late principal, Dr. 𝗓𝗏𝗪, and he is initiated such type of events. So thank you once again all.
Yes,
Thank
ma'am.
you, ma'am.
Thank you so much, ma'am. So I think somebody is asking.
Okay.
Hello.
Okay, no issues.
Hello. Please ask.
Okay, ma'am.
Okay.
You can wind up.
Okay, thank you.
Okay. I think there is no one. So thank you so much, ma'am. Your expertise and valuable insights have had a great value to this FTP. And thank you for delivering such an informative and very inspiring session. Thank you so much, ma'am.
Okay, thank you.
Okay. So dear participants, please join again tomorrow at 6 p.m. And your attendance link is in our WhatsApp group. So please don't forget to put your attendance. And tomorrow we have speakers